Okay, continue our talk about relations. This is video number 2, and today I want to review not just heterogeneous relations properties. I want to review properties of relations such as homogeneous relations properties and heterogeneous relation properties. And we started the group of the properties which called uniqueness properties. And the first property of this group is injectivity, injective. So a relation is called injective if for all x and z belongs to this to some set x, and all y belongs to set y, if x related to this y and z related to this y, then x equal to z. This means that for every second element of the pair of the relation, we have only one element of x. So x is determined by y, and in this case y is called the primary key of R. Okay, and let's start to implement this. We can take some type signature of here, and I just need to change one thing here, because we're talking about relations at any kind of binary relation, not just only AND relation as we talked in the previous video. This means that we can have different types of our domain and codomain. And of course I need to have ordering for both of them, because they represent them as a sets. Okay, and we can go to definition of injective property. We need to have here some relation, how we encode relation. Let's remember. So we have these definitions, this definition of the relation. There we have two sets, the domain and codomain sets, and we have also the graph, actually the pairs of these relations. All these three things represented their sets. And let's again go to our implementation. So I think we need to input match, of course, our relation. We have these three sets here, and what they need. So we have the image of our set. If I take every element of image of the set of our relation, if I take every element of image of my relation, and I check just how many, for every element of this image, I just check how many related x it has, and it must have not greater than one corresponding x. Okay, let's write this in code. So we have our image, and we take every element of this image. So actually I can't use this comprehension here, because our image is represented as a set, I think. So we have image function. Yes, we have this image function. So if you don't remember what is the image, we take the relation, some relation, and give all the y's which are presented in the parents in the ordered pairs to this relation, all the second set of all the second elements, and we have this function. I think this is not a very good implementation. We can use some set functions here, but I do transfer into this. Okay, maybe I will refactor this in the end of the video. By now we can just use this function to get this set of the second elements, actually the image. Okay, I can't use the list comprehension, but I can use map function. Let's look at this. I think we have what we have this set module, and it has a map function, so we can map the set. Also, I think set is a foldable. Yes, set is a foldable. That's why we can also use O function for this. So we take our image of the relation of our relation. So I think we need this relation at all here to better match it. And I think, I don't know, we need this better matching or not, we will see later. So we take the image. Next, they use the map function for this image, and this will be lambda, which takes every element of this image. Actually, this is y. This is some second pair element, and we want to check. So at first they need to extract all corresponding x's. So we need to have some helper function rel to y, which takes some relation and also it takes some element, the second element, and produce some set of type A. So this will be, I think this will be the axis, actually the set of axes. And what is definition? So related to y. Related to y. We need to have the relation, which we need to better match, I think, here. We have this relation, we have x's, we have y's, and we have graph. And we have this y. So at first we need to take this set G and filter it with some, so let's look at the filter function. As filter, we can filter our sets. We need to provide filtering predicate here. We have this element x and y, and they need to filter only this y's that is equal to our y. I think like this. after they do this filtering, they can map. And how we do the mapping? We just provide some lambda function which takes x and y and produce x. Also, we're not interested in this y here, and also we're not interested in this x here. Okay, yes, I think this should work. This function will return to us related to y elements as a set, and now we can here we will need to check the cardinality of this set. And to check the cardinality, we can do the image function. So I check it like this. I need to say that length of my relation is equal to, not relation, of course, the length of my relation to y is equal to 1. Okay, like this. So I try to compile and have this error. I have some typing errors here. I think we need to improve it like this. Oh, this lambda sign, why it's here? It must be here. Okay. Here, of course, then I mapped all my image to these booleans. I need to check that all of it holds. So I need to use all function here. So why do this mapping? I can use all, and here I can use this predicate. Yes, why not? Rel to y, it's need two parameters. It needs our relation and it's need our y. Okay, we're done. Now I think we can try to build some relations with our rel constructor. Oh, not why we use a rel constructor. We can use from list constructor. We have this function which allow me to build any type of relation. Okay, and let's build some. Rel from list. Let's look at its type again. So we need to provide two lists. The first list is domain. For example, I can model relation from integers to some chars. I think like this. And actually the relation itself is a set of some pairs. For example, like this. Okay, oh, it can be 1 to be. Okay. What I'm writing. I need to write a tuple. I need to write a list of pairs, of course. Like this. Okay, and they built our relation and they can try to check it. Try to check it for our injectivity property, injective error. And it is injective, as you can see, because every x is determined by y. But actually injective it or not. And yes, this is injective relation because this is not a function, so the two y's, two different y's, I think can map to the same one, x. But if I add, for example, something I think like this, and the will be in the situation, then they have same y, but two different x's. In this situation, our injectivity, you can see, is broken because two same y or a's maps to two different x's. Okay, next type of the relation is the functional relation, also called right unique or right definite or univalent. You can see its definition here. So such a binary relation is called a partial function, actually. And for such a relation, x is called a primary key of R. So x is uniquely determined y. This means that there is no two pairs of the same x in this relation. And I think implementation of this relation is exactly like this. It is somehow symmetric case, so we can use this code and a little bit modify it. So we actually interested in all y's. And here the filter. So actually we need this x here as a parameter. Then it filter all the x primes. We're not interested in y. And they have condition that x is equal to x prime. Okay. And we have this relation to x. So we collect all the related to x, y's. And they expect that... Oh, what's the problem? Oh yes, problem in type signature, we need to provide a here. They have this type a here as a domain set. They're interested in the element of the domain set, that's why. Okay, next error. Of course, here we return a set of b's, not a's, because this is y's. Okay, we're done. And now we can use injective here. I think this will be same, but we do functional property. And what they need to say that all related to. So here we need to say not image. To take not image, we need to take active domain, I think, yes? Have active domain here. We take active domain and the which we take the related to y, so this x. Okay, and we just filter. We just check that all x's have exactly one y. And the done. Now we can try to check functional relation. For example, for this relation, is it functional? Oh no, it is not functional because we have two ones here, which leads us to we have exactly two same x's here, which leads us to different y's. So we have two pairs. They're the same x. Let's fix this, for example, like this. In this case, this became a functional relation. Okay, next type of relation is one-to-one, and this is just an injective and functional relation. So we can very easily check it with injective error and functional error. Okay. Next type is one-to-many. This is the relation which is not functional and injective. Oh. Okay. Why it not compiles? Okay, like this. The next guy is manytoone. This is not injective and functional. Okay, next is manytomany. It is not injective and not functional. Manytomany. Not injective and not functional. Okay. I need to put type signature. So the next guy is total relation. This is somehow like a total function that for all x it must be defined. So there must exist some y for this x. And I think we can very easily check this. So we need to take this relation, take active domain of this relation, and it is total if this active domain equal to the domain of this relation. And how can, of course, we can take this domain from our relation via pattern matching. So we take it like this. Okay, and this is a total relation. Let's check. Total. Okay, it is true because for every 1, 2, 3 it has some element, and now it is not total. Okay, next guys, surjective relation is also called right total or onetoone relation. That means that for all y in y, there exists an x in x such that it's related to y. So in other words, for every second element, we have some first element. And the definition, I think, is exactly the same like for total, but it's somehow symmetric. So we need to take the image, I think, of our relation, and this image must be equal to domain, to codomain. Okay, we can test for surjectivity like this. And this is not surjective because we need to provide something for C. Okay, and now it is surjective. By the way, these two properties are called totality properties. And these properties from injectivity to injectivity functional one-to-one, one-to-many, many-to-one, many-to-many, this is uniqueness properties. Okay, next type is a function. That function is a relation that is functional and also it is total. Okay, this is function. Injection. So functional injective. Injection. I'm care about naming clash, but there is no naming clash here. This is a functional. This is a function relation and also injective. And injective relation. Let's add that signature. Okay, and next to guys is surjection. Surjection is a function which is surjective, and bijection. The bijection is a function that is injective and surjective. Okay, very simple. Okay, this was video number 2 about relations, about heterogeneous and homogeneous relation properties, and I think the next video will be about operations on these relations. So guys, thanks for watching, push like, push subscribe, write comments, and see you in the next video. Bye bye.